Here we go, buckaroos and buckarettes, on page 274. Now, what I'm asking you to do here, Miss Barnes, is write the word equation right on top of the formula equation, okay? So you can demonstrate to me that you're not missing any of these little concepts here. So sodium's pretty easy. Sodium, Na, solid, you write with a little S there, okay? And then the chlorine gas. Now, I've been around the room a couple times, and I have seen some people not writing this chlorine as diatomic. You have to remember that. If you make that simple mistake, this equation won't balance. When we get into the next chapter and on into the course, you're not going to be asked, you're not going to be given the products, the reactants and the products. You're going to be given the two reactants and asked how much, for instance, how much sodium chloride will be produced. Well, it's based on the molar ratio in the balanced chemical equation. You can't balance the equation if you don't have this chlorine written as diatomic, and you can't answer the question. You can't really start the question. So you have to pay attention to these details, okay? So now here we're going to produce solid sodium chloride. Well, this is about as straightforward as it gets. Sodium chloride, right? Now, the problem, well, we put a little S here. The problem is we started out with 2 because it's a diatomic molecule. Chlorine exists only as diatomic molecules, right? So we've got 2 chlorides here, 2 chlorine atoms here bonded together. We're going to have to put a 2 here. I'll make it red so it'll be obvious for you. So we got 2 here. Now that's going to force 2 in front of the sodium. Should be no question about that, but that's the way we have to do it, okay? Now here we get into a little bit a little bit more sophisticated idea here. Solid copper, that's pretty straightforward. Symbol for copper is Cu. We just write the little S. Now the aqueous means that this is dissociated. It's in water and it's dissociated. Here you have to remember that silver is an exception in the transition elements in that they don't give you a Roman numeral. The reason they don't is because silver is always 1 plus, so they don't need to. I wish they would do away with that rule and give you the 1 plus, because you wouldn't make that mistake. I mean, it would eliminate one mistake anyway. So silver nitrate then is 1 silver to 1 nitrate. Now I'm not writing this charges up here because it gets too busy, but what you understand is this silver's 1 plus, nitrate's 1 negative, so it's 1 to 1 ratio, okay? And now this thing tells us that this is going to produce aqueous, I just didn't write it out because I didn't have room there, aqueous copper 2 nitrate. Now, what kind of reaction is this when the copper displaces the silver? So we know we got copper nitrate. The uninitiated, the unattentive, the formerly lousy chemistry student doesn't realize that that 2 refers to the charge on the copper. Hello? So that means the copper is a 2 plus. The silver was a 1 plus. So the formula for copper 2 nitrate, we have to have 2 nitrates because the nitrate doesn't change. The nitrate is still 1 negative. The copper is 2 plus. The silver was 1 plus. So that changes the formula. Now, that leaves the silver out in the cold, okay? And it is written as solid. So when it's written as solid like this, this means these metal atoms over here have all their electrons, they have a 0 charge. All their electrons, they have a 0 charge. When they have this 0 charge, they will not dissolve in water. They fall straight to the bottom, okay? Because the water has no attraction for them. And that's when we get a little bit later, it talks about like dissolves like in solutions. It means that polar solvents dissolve polar solutes. And as long as these things are neutral, they're not going to dissolve in water. As soon as they obtain the charge, they will. The water is attracted to them, okay? Now what really happens here is this copper, if you look on page 286, is more reactive, is higher on the activity series than the silver. So it forces its 2 electrons onto the silver ions, right? 1 copper forces 2 electrons, 1 on each silver, and that makes the silver 0. It has to accept the electrons, loses its charge, falls to the bottom of the reaction chamber. The copper goes up into solution, okay? So what we really have here is a transfer of electrons, okay? Now, what this aqueous means, and you don't write it, it means that you have silver ions here and you have nitrate ions here. Okay? Here you have copper ions here. What is the copper ion? It's copper 2. Got it, Miss Clark? And here you have 2 nitrate ions. Right? Okay? So we have to balance it, and the only thing out of balance at this stage is the nitrates, right? So what we do is we put a 2 here to give us 2 nitrates on this side. We got 2 on this side, but now we've got 2 silvers. So we have to put a 2 here. And I believe that baby's balanced. Right? What kind of reaction is this? Somebody? Single replacement or single displacement. Okay? This one up here is what? Synthesis. What else? How else might you see that? Combination. Okay? So this is single replacement or single displacement. Depends on the textbook. Okay? Okay, they used to say displacement, and then they thought that the high school students weren't smart enough to understand displacement, so they said replacement, not realizing it wasn't going to help. It's a matter of paying attention, okay? So here we have solid iron. Can't fool me. Iron is Fe. What does the 3 mean? It's a 3 plus ion, right? So we're going to have iron oxide. Iron oxide. The 3 tells you there's a 3 plus on the iron. Okay? So the way you would write this, without writing it down, you know oxygen's always 2 negatives. You crisscross these. That makes FeO3. Okay? And the 2 goes to the iron. That's iron 3 oxide. That's common rust. Okay? You're technically not to write these. Okay? These charges. All right, and we're going to combine this with carbon monoxide, which I suppose that's a gas. And I suppose this is a solid. Is it right? Is it not? Yeah, solid. Okay, and so then what we're going to do is we're going to decompose this iron 3 oxide into solid iron. Now, when we say solid iron, what happened to that iron atom? Gained 3 electrons. The charge here is 0. The charge here is 3 plus. Okay? So this iron, where are you going to find this iron? Huh? You're going to find it on the bottom of whatever the chamber is that you're doing this reaction in, right? It says a blast furnace. You're going to find it on the bottom of the blast furnace. Suppose this is the way you would recapture iron from a pile of rust. But anyway, so we balance this thing, and what are our problems here? I'm looking at this, and right off the bat, I'm not sure how you balance it. I know I've got 3 oxygens here, and I've got 2 over here, and I got a 4 over here. Let's see. And the iron's out of whack. So you're saying put a 2 here? So you're saying put a 2 here. Now what does that do for you? Well, I know, but okay, so we've got 1 carbon, so our oxygens are out of whack. We got 2 over here and 4 over here. Okay, so what are we going to do? You say put a 3 here, and that gives us 3 carbons, so we got to put 3 here. That's 3 carbons, and so now we have 6 oxygens, and 3 and 3 is 6 oxygens. She looks balanced. By the way, when an element here gains electrons, it is said to be reduced. Okay? If it loses electrons, it's said to be oxidized. And so that would be the opposite case when this iron, pure iron, combines with oxygen, right? So it goes from iron with all its electrons to iron missing 3 electrons